This lecture is about the stage 3 of carbohydrate metabolism, tricarboxylic acid cycle, or just TCA. Tricarboxylic acid TCA cycle is one of the most important things for me is that begin and end with the same substrate oxaloacetate or OAA. There are 8 steps in TCA cycle. The main substrate and product of the following reactions of the cycle reveal the chemical structure potential for the release of CO2. As you see, the TCA produces 2 CO2 per cycle from the complete oxidation of acylic coenzyme A. In other words, each cycle of the TCA cycle completely oxidizes acylic coenzyme A. 2 cycles of the TCA cycle therefore account for the complete oxidation of 1 glucose 6-phosphate or 1 glucose or 1 glycogen. Okay, let's break down TCA cycle. Step 1 or reaction 1 involves the donation of 2 carbon acid group from acylic coenzyme A that combine with the 4 carbon oxaloacetate intermediate to form citrate in the citrate synthesis reaction. This is the chemical structure of the substrate and product of the first reaction of the TCA cycle. The first reaction, catalyzed by citrate synthase, is important as it combines a 4-carbon oxaloacetate and a 2-carbon molecule, acetic acid, to form a 6-carbon citrate. The structure of citrate is also very important as it is a 6-carbon tricarboxylic acid structure, and this product gives the cycle name tricarboxylic acid cycle TCA. You do not need to memorize this slide for this course, but I would like to show you the chemical structure of the substrate and product part of the all reaction of the TCA cycle. Reaction 2 or step 2 is involve the conversion of citrate to isocitrate. Reaction 3 is catalyzed by isocitrate dehydrogenase, which performs an oxidative removal of 2 electrons and 2 protons, decarboxylation, removal of CO2, thereby reducing NAD plus to NADH plus proton and producing CO2 from the carbon 2 carboxylic acid group. The product alpha-ketoglutarate is an important TCA intermediate as it is a major location for amino acid entry into mitochondrial respiration. Reaction 4 or step 4 is really a multi-enzyme complex reaction like that of the pyruvate dehydrogenase complex and involve the oxidation of alpha-ketoglutarate causing the reduction of NAD plus to NADH. So at this time 2 electron and only 1 proton removed. However, our class just using NADH plus 1 proton instead of NADH. The addition of coenzyme A and decarboxylation forming succinyl coenzyme A and producing CO2. Reaction 5 involves the conversion of succinyl coenzyme A to succinate by the enzyme succinyl coenzyme A synthetase. This reaction also performs a substrate phosphorylation of either guanosine diphosphate GDP or ADP, forming GTP or ATP. The phosphate group comes from free inorganic phosphate from within the mitochondrial matrix. The free energy for this phosphorylation comes from the removal of coenzyme A, regardless of the regeneration of GTP in the reaction. Convention is to refer to the succinyl coenzyme synthesis reaction as an ATP regeneration reaction, as GTP is really readily converted to ATP by the enzyme nucleoside diphosphate kinases. Those ATP and GTP have equal free energy equivalents. Reaction 6 is catalyzed by succinate dehydrogenase. Just based on the name of the enzyme, you should be able to predict the chemical event of this reaction. Dehydrogenase enzyme remove electron and proton from the main substrate, oxidation, and typically they are donated to either of NAD plus or FAD, causing their reduction, meaning gain of electrons. In this reaction, the remove 2 electron and 2 proton cause the reduction of FAD to FADH2 and producing fumarate. Reaction 7 involves the simple hydration of fumarate to produce malate via the enzyme Fumarise. Note how the additional of proton and electron of water provide added proton and electron which can be subsequently removed in later reaction. Within the TCA cycle, such removal occurs in the next reaction. Reaction 8 is the final reaction of the TCA cycle where oxaloacetate is produced via malate dehydrogenase. Yes, oxidation reduction is involved here and 2 electron and 2 proton are removed from malate oxidation and used in the reduction of NAD plus to NADH plus proton. The 4-carbon oxaloacetate is now available to receive the 2-carbon acetate group from acyl coenzyme A with the TCA cycle start again in the production of citrate. So 2 carbon plus 4 carbon is 6 carbon. The complete TCA cycle look like this. However, this slide more important for you than the previous slide of the chemical structure of the substrate product of TCA cycle. The reaction of the TCA cycle results in the production of 3 NADH plus proton, 1 FADH2, 1 GTP or 1 ATP, and 2 CO2. The molecule GTP is guanine triphosphate and is intercompatible with ATP, so it is counted in the ATP tally of metabolism. NADH plus proton and FADH2 are the major product of TCA cycle and harness electron and proton for use in the ETC. For every glucose molecule that is completely catabolized to CO2 and water. The 2 pyruvate molecules that enter the mitochondria require 2 cycles of the TCA cycle. So 1 cycle each. So net yield of the 2 acyl coenzyme A, 4 CO2, 6 NADH plus proton, and 2 ATP, 2 FADH2 from TCA cycle. And these are glossary words. Thank you.